This is the lecture on finding the limits of integration when they are functions. And here is the first rule. Make a sketch. You have to do that. Now, if Fubini's theorem is satisfied, you can perform the integration in any order. And Fubini's theorem states that if f is a continuous function, and if any functions that appear in the limits of integration are also continuous, then you can switch the order of integration. And that's sort of instructive to look at how that's done. So here is an integral with respect to x and y. dy is the most inner integral, it's the most nested one, and its limits can be functions of dx, of x. Now the outside integral, in this case with respect to x, must have constant limits, and that's shown here with this a and b. Now say that the g's are continuous and f is continuous. We can switch this, so we're going to be doing the integral with respect to x first, but we won't have the same limits. We now have to have limits for x that are functions of y, because y is the most outside integral and its limits are continuous. Are constant. If all the limits are constant, then finding and reversing the order is trivial. Here we do x first, and x has limits of x of 3 and x of 5, and y has the limits 2 to 4. We can switch the order here because the function xy is a continuous function, so when we switch the limits, we're doing y first, but make sure you put those limits there, and then dx will have limits 3 to 5 again, and those will have to be written on the outside. Here's a procedure for finding the limits if they're not constant. And there will be an example given in a minute. So first thing, first sketch the region. Then pick one variable to have constant limits. Say that variable is x. So you pick x to have constant limits. You find its maximum and its minimum values, and this will be the last or the most outside integral that's performed. Then looking at your sketch, you draw a line parallel to the y-axis. And you find an expression for the curve as the line meets, as the line enters the region, and you find another expression for the curve as the line leaves the region. If you're doing the integral in another order, in the other order, you would then pick y to have constant limits. You'd find its maximum and minimum. Those would be the limits of the most outside integral that you perform. Then you draw a line parallel to the x-axis, and you find an expression for the curve as the line that the line meets as it enters the region, and then you find an expression for the curve that the line hits as it leaves the region. We use a similar procedure for triple integrals, but there's one additional step. So here's an example. It's for a double integral. Remember that this xy that is shown here without labels is in the xy plane, and the function values themselves, which is a function of x and y, are graphed in the z direction. So we've just broken this out for convenience into a two-dimensional plane, but it really is the base of the integral that we're performing. So the first rule is make a sketch, which has been done, and then pick maximum and minimum values for x. Well, I'm saying x is constant. Okay, so its minimum value is -2, its maximum value is 2, and you can see that is the most outer integral, and it will be the last one performed. The next step is to draw this line parallel to the y-axis. And now you must find an expression. Let me draw that on there. Now you must find an expression for the curve. In this case, it's just that horizontal line. So here's this line going through the region of interest. When it comes into the region of interest, it hits a straight line, y equals 0. That becomes the lower limit of integration. Then the line leaves the region, so to speak, and it hits this parabola, minus x squared plus 4. That's the expression for this curve that the line meets as it leaves. Obviously, no matter where you draw it, you're still going to hit that same curve. All right, so minus x squared over 4 becomes the upper limit of integration. You can see this is set up properly because y is the inside integral here, and it has limits that are functions of x, and x is the outside integral. Now let's do it the other way. In this case, we picked y to have the constant limits. So its minimum value is 0, its maximum value is 4. So y is going from 0 to 4. That becomes the outside integral, and it will be performed last. Then we draw a line parallel to the x-axis, right here, and we observe what the curve this encounters as it enters a region and the curve that it encounters as it leaves the region. Now this curve was y equals x squared minus 4. We have to solve this for x in terms of y, so we end up with x equals, I guess it was plus 4, I'm sorry, 4 minus y, and there will be, of course, plus and minus signs when we take the square root. Now we've solved this for y. Where it enters the region, x is minus 4 minus y to the 1/2, the square root of 4 minus y, and that will be the curve, this curve from here down to here. Now when it leaves the region, x is the square root of 4 minus y. It's a positive value. Let's see, so you had to do a little bit of algebra to find those limits. Again, finding the limits, this is easy. Sometimes finding the limits is very hard. But now that we found those limits, they become the limits of integration here. X is performed last. Notice that its limits depend upon y, and y is the last integral. I'm sorry, I think I said that wrong. The x integral is performed first, and its limits depend upon y, which is performed last. So now just to evaluate these and show you that you get the same answer. So in the first case, we have the inner integral on dy. The limits depend on x. So you carry that out first, and now when you're done carrying that out, you have an integral that depends only on x, which you can easily evaluate. Although I made a note here that the signs were fairly painful when I did this, and I ended up, because of arrogance, had to do it several times. So if you take your time and do it, you'll come up with an answer of 32 over 3. Now in the second way, we have this inner integral for x. Its limits depend on y. So when you carry that out, you have an integral that depends only on y, and you get the same answer. Here's a problem from the homework, and the idea is to switch the limits around. So I'll just show you how to do that. So first thing, of course, make a sketch. In this case, the outer limit is y, and y is going from 0 to 3, and that's a constant. So I'll just say do something like this. So this will be my x-axis and my y-axis. And y is going from 0 up to 3. Now what is x doing? There would be a line, there'd be a line parallel to the x-axis. This is how those limits were arrived at. That's a bad preposition at the end of that. Okay, so here's the line coming into some region, and the first thing that it encounters is the line y over 3. So y over 3 is just a straight line, right, with a slope of 3, looking something like that. And that's the line that it hits as it comes into the region. Then its maximum value is, then as it leaves the region, it hits the line x equal 1. Here's a line x equal 1, like this. Okay, so as it enters the region, it hits the line y equal 3. As it leaves the region, it hits the line x equal 1. So here's the region that we're integrating over. Y going from 0 to 3, x going from y over 3 to 1. Now the idea is to turn this around so you integrate with respect to y first. So if you look at this number's 1 right here, then we want x to have constant limits, and it's going to go from 0 to 1. This is its minimum. Here's its maximum value. Now you draw a line parallel. I'm trying to do a different color here, have a green. You draw a line parallel to the y-axis to determine the limits in y. And okay, when it enters the region, it hits a line y equals 0. So for y, the lower limit is going to be 0, and the upper limit is going to be this line right here, this slanted line right here. Right now that line is written as, or previously it was written as y over 3. We can solve for y, and y is 3x. So when it leaves this limit, it leaves the region, it will hit the function 3x. So now the integral, okay, the outside one is going to be an x, and it'll have the constant limits. The inner one is going to go from 0 to 3x, and now you would do y first, and then you would integrate with respect to x.